Okay, good morning. I'm sorry for the slight delay here with the technical issues, but everything should be up and running now, so you should be able to hear me. If you can give me a thumbs up, that'd be great, so I know that that's in fact the case. Very good. Thank you. Okay, so what we're going to do today is start with chapter 9, and we're going to talk about linear momentum and collisions in chapter 9. We already introduced linear momentum, but we're going to reintroduce it here. And then we're going to go into the concept of impulse and how impulse is transferred in collisions. So let's start with linear momentum. So the goal of this chapter is essentially what makes a baseball change direction when there's an impact with a bat. That's one way to summarize this entire chapter. We don't necessarily want to care about the details of the interaction of the baseball with the bat. We just want to know what is the ultimate effect on the baseball. Before the baseball hits the bat, the ball is in some ballistic trajectory. After the baseball has been hit by the bat, it's again in some parabolic motion. It's moving under only the influence of gravitational force, maybe some drag. But what is it that makes the direction change? So to do that, we're going to introduce the concept of linear momentum. And momentum, as we already introduced earlier, is mass times velocity. So a momentum in vector form, so linear momentum is mass times velocity. So in vector form, or in mathematical form, it looks like this. So we can have two different things that have the same momentum. For example, if something has a large momentum, it could be large because the mass is large, like in the case of this tanker here, or it could be having the same momentum at a much smaller mass due to a large velocity. So it's the combination of mass and velocity that is determining the momentum. Combination of mass and velocity. And you see that it's slightly related to kinetic energy in that sense. Kinetic energy also combined mass and velocity. In this case, it was velocity squared, so it was the speed that was only relevant, the magnitude of the velocity, not the direction of velocity. So this is a scalar quantity, whereas this is a vector quantity. And you also see that it's not exactly the same. So the kinetic energy has only one factor of m with two factors of e, whereas in the momentum you get one factor of m and one factor of e. So if we write the kinetic energy as we've done before as well, we get the momentum squared over 2m. So the kinetic energy depends on the momentum. So kinetic energy depends on the momentum, but it's a different quantity. It's not entirely it's not a one-to-one correspondence. Also note that I'm talking about momentum. I'm not always mentioning the word linear momentum. It will typically be clear when we're talking about linear momentum and when we're talking about another kind of momentum, which we'll introduce later. That's angular momentum. Obviously, angular momentum will involve some angle, and linear momentum is if something is moving along a line, and so that will be when it's about the velocity. We've also already introduced momentum earlier when we talked about F equals mass times acceleration, right? Or as we actually wrote it, A is F over the mass. So the acceleration is determined by the force, and the force over the mass is what gives us the acceleration. By writing this in terms of momentum, we could actually write this as the force is the first time derivative of the momentum to the time. The first derivative of the momentum to the time. So this is Newton's second law using momentum. And this is actually going to be the crucial law that we'll use today for our discussion about impulse. So it's telling us, so even though of course kinetic energy is important, the main thing that this is telling us is that the momentum changes based on the force that is applied. Just like mass times acceleration, or just like acceleration changes based on force over mass, the momentum changes based on the force that is applied. So Newton's second law, therefore, is often also stated without mass times acceleration. It says that a force changes an object's momentum. Okay, an equal force, therefore, will cause an equal change in momentum, but for an object that has a smaller mass, that will mean a larger change in velocity, all things equal. So if we have, let's say, I think there's a slide for that. Let's see if we go. I don't think there's a slide. Well, maybe this one. No, not this one. So no slides for that. Let's come up with an example. If we have, for example, this oil tanker here, which obviously has a very large mass, we can apply a very large force to this oil tanker, which will cause a certain change in its momentum. But because it has such a large mass, that will actually correspond to a fairly small change in velocity. If the oil tanker was empty, or if there's a smaller ship, the same tugboats that might push this oil tanker and apply the same force could cause a much larger change in velocity for a smaller boat or for an empty oil tanker. So this is how, of course, the same force applies, but there's a difference in the effect on the velocity, even though the change in momentum is going to be the same. So this example of the oil tanker, that's where, of course, the mass is large, the velocity is small. Another example where we actually have the opposite situation, and I by no means want to imply here that the momentum of an oil tanker is the same as the momentum of gas molecules in a bottle, but gas molecules in air, or even in any gas, have a much smaller mass but have a larger velocity, and that allows them to have a certain amount of momentum. And momentum, in fact, the momentum that they transfer when they interact with the walls is actually what causes the pressure in this gas. So that's momentum, mass times velocity. It's the product of the two, so both of those are important. A change in momentum will typically, of course, come from a change in velocity, not a change in mass. Although, again, as we talked about earlier as well, if we have a spacecraft or a rocket that is being launched, then the change of mass does actually play a role, and that changes some of the equations a little bit. So the next concept that we're introducing here is impulse. So after talking about linear momentum, now we're going to introduce impulse. And impulse is the integrated force over a finite period of time. Integrated force over a period of time, and let's call it delta t. But of course, we're going to introduce it as an infinitesimal quantity, and this impulse we're going to give the symbol J. So the amount of force over a tiny interval dt is going to be the impulse. So the impulse dj is the force times dt. So if we have a force pointing in this direction, if that force applies for an interval dt, then of course we'll have, I'm just drawing vectors here. It doesn't really matter what I'm drawing, but then we'll have a dj as the impulse. So the impulse will be in the direction of the force, and in this case, for an infinitesimally small time element, this force will be constant, and the impulse will be in the same direction as the force. Now, the interesting thing will, of course, happen when we integrate this over time, right? So if we, let's say, have a force that changes direction, so the force first points in this direction, and maybe it changes direction and becomes larger, and then it becomes smaller again as it continues changing direction. So let's say that the force kind of changes like this as a function of time. So then, and this is the time interval delta t over which this happens. What's going to be the impulse now is going to be the integral of the force as a function of time dt. And that will be from time t1 to time t2. Let's imagine we're starting here at t1 and we end up here at t2. So essentially, the impulse will become the average direction of the force multiplied by the duration over which this force applies. So this is going to be the average of the force times the period of time over which it applies. We can, to some extent, interpret this in a variety of different ways. We can choose different averages if we choose different delta t's, if we choose different time intervals. So let's say we have a force that only changes in magnitude, and it changes in magnitude like this. So there's a couple of different ways we can take this average. We can say, well, let's say that the force actually on average was this strong, and it applied for this amount of time. So that's our delta t1 with our f average 1. Or someone else might make a reasonable argument that maybe this force is actually, I'm going to put this all in a much narrower interval here. That's going to be my delta t2 with f average 2. Or someone might say, well, this is actually probably best modeled by a force over a long interval delta t3, and that's going to be the average force that applies over that long interval. The important part is that the product of delta t and f average, or in other words, the surface area under this curve, is the same as the product of this blue average force and delta t. It's the same as the product of the green average force and delta t. And it's going to be, of course, exactly the same as the integral underneath the curve, the surface area underneath the exact curve. But what the average forces allow us to do, and the delta t's allow us to do, is sort of ignore the exact behavior of the force, and instead we can just replace it by two numbers, an average force and a delta t. So this allows us to average out the details of f as a function of time during the time interval delta t. So if we go back to the slide now with the baseball bat and then how the interaction happens here, we don't necessarily care about the details of this interaction. So, I mean, there might be a time when the baseball deforms slightly and the bat bends a little bit, and that causes the force to sort of slowly build up over time, and then there's going to be a maximum to the force. And at some point, the bat will bend back, the baseball will expand again, and then at some point the baseball loses loses contact with the bat, and so the force will be zero again. So the important thing is that we know that in this situation, the force will look something like the black curve here. It will start at zero, it will increase, and then it will decrease again. The overall effect is just the product of a force, an average force, times a delta t. And that should allow us to do all of the calculations that we want to do based on that impulse, which is the product of the average force and delta t. So what is happening is that the baseball is acting through the impulse that it imparts on the ball. Now, of course, the next step is going to be how do we do something useful with this impulse? Well, we can look back now at our expression here, or F or force is dp dt. So if we write everything we've learned till now, we have dj is F of t dt, and we know that F is dp dt. That means from the second one we can write that dp is F dt. And if we take an integral, we find that this is, so the integral of dp is the integral of F dt. So that is going to be delta p, the change in momentum, is equal to this integral. Well, that's the integral that gave us the impulse. So the impulse is equal to the change in momentum. And that's going to be the important relationship that we now want to use. So in the case of a baseball, let's say we have an incoming momentum P initial, then we know there's going to be an outgoing momentum P final. So the change delta P, what am I doing here? That's the wrong direction. So the change to get from the incoming momentum to the final momentum, that is going to be the impulse. And that impulse will of course point in this direction, such that J is P final minus P initial. Or in other words, P final is P initial plus the impulse. So the impulse changes the initial momentum to get the final momentum. So we've looked at this impulse as in a couple of different ways now, right? We've looked at it in a way as a detailed integral, which we could calculate exactly if we knew what the force behaved like as a function of time. We've looked at it as an individual quantity J, and it's going to be a product of force times time, so it's going to be in newtons times seconds. And we've also looked at it as a product of an average force and a time interval. So now we can, of course, look at, we can use any of these three pictures depending on the question that we're asked, right? So let's go back here. So we can look at it as, for example, as a tennis racket, but I actually wanted to get to the soccer ball example here. So we can think of this now as someone who kicks a soccer ball causes a delta P, a change in momentum for that soccer ball. And that's determined by the force and the time interval. I wish they had used delta t here instead of t0. So that is the change in momentum is determined by the product of the force and the time interval. If that person now kicks the ball and has a contact with the ball that is twice as long while maintaining the same average force, and of course we'll end up having twice the change in momentum. And if, for example, we start with a ball from rest, that will give it a final momentum that's twice as large, and for a constant mass for the ball, that will of course mean that the ball isn't going twice as fast, right? So that's how we're going to use impulse. It is the instantaneous change in momentum that is imparted to an object. We can look at that now to solve other problems too. So the textbook has an example for this the Barringer crater in Arizona. It is an impact crater from a meteorite that landed in Arizona, and that of course caused that crater. Based on some assumptions about the meteorite, we can actually determine what the impulse must have been, and what the change in momentum would have been for that meteorite. So we can, and that will allow us then to determine what the average force is that the meteor imparted on the Earth, or of course the other way around as well, because Newton's third law applies. The force that the meteor exerted on Earth will be the force with which the Earth pushed back on the meteor. And what we're actually calculating here is going to be the force from the Earth on the meteor to change its momentum. So let's look at that for a number of for a couple of different values. Well, for one set of values. So if we start from an initial, so let's meteor impact. So if we start from an initial velocity, that's 1.28 10 to the 4 meters per second. And we're assuming here that this velocity is perfectly perpendicular to the surface. And the final velocity, if we assume that final velocity is 0, because the meteor is somewhere under the crater, under the ground right now. We can assume a couple of other things. We can determine the density of the meteor that actually struck. So that's, let's say it is determined to be 7,970 kilograms per meter cubed. And let's say that we know that the radius of the meteor is 25 meters. The problem in the example in the textbook gives a couple of other values which are actually not used in the problem, but one of the key aspects which might also be useful on the midterm is to be able to figure out which quantities are given that you need to use, and which quantities are given just to confuse you. So from the density and the radius, we can determine the mass by going through the volume of a sphere, which is what we'll assume, since we don't know anything else. I mean, maybe that meteor had a shape that wasn't an exact sphere, but a sphere seems like a good approximation. So the volume is 4/3 pi r cubed, and together with the density, we can get to the mass, which is going to be rho times v, right? So that's the mass. We've got the initial velocity and the final velocity. So with that, we can now calculate delta P, which is the final velocity minus the initial velocity times m. And that is going to be the impulse that the Earth applies on the meteor. That's the impulse that causes the meteor to go from an initial velocity that is in the negative y direction here to having a 0 initial velocity. So with with a final velocity of 0, this is of course equal to minus mv initial, but we have to think about the fact that we're working in vector quantities here. So I'm going to write my vectors here. So this is actually minus m times vi, but this is going to be m times vi in the y direction because vi is in the negative y direction, right? So the impulse that the Earth applies is in the positive y direction. So it's actually pointing in the direction of this f of t here. And that's of course because this impulse, j, will be the integral of some force f of t over a time interval t between t1 and t2. So this is one of those cases where the impact will have a certain force as a function of time. So this is the force that the Earth applies onto the meteor. And that force will change over time. And so we could calculate now from our impulse, we could calculate what is the average force over an average time interval. So if we assume that delta t, let's see, assume delta t is 2 seconds, then our average force will be our impulse over delta t. So it will ultimately be m times vi over delta t in the y direction. So that's going to be the average force for a particular choice of time interval delta t. We could pick a different time delta t. I mean, this is just in the assumption, right? If delta t is 1 second, then the average force will be larger. We don't know the exact time duration that it took for this meteor to interact with the Earth, or to go from an initial velocity to a final velocity of 0. But we can assume that 2 seconds sounds reasonable. And if we assume 2 seconds, then that gives us this particular average force, right? We could do something more accurate if we wanted to. We could take a functional form here. We could assume that the f of t is some maximum force times, let's call this some Gaussian distribution, a symmetric exponentially decaying peak with minus t squared over 2 tau squared as a magnitude. So we could use that and we could calculate f max. But there really isn't all that much more that we get out of this. The f max would be approximately equal within a factor of 2, for example, to the average force. So if all we're interested in this derivation, which inherently we're limited because of the knowledge that we have, if all we're interested in is the order of magnitude of these forces, then this approach actually gives us an order of magnitude for the force that the meteor will experience. And we can actually plug in the numbers. If you take that mass, initial velocity, and final and the interval of time 2t, then you will find that the average force, this average force is 3.3 times 10 to the 12th newtons. So of course it's a very large force, and that's because of both the large mass and then the large velocity, which has to be brought to rest in a short time interval. So, so the impact might have looked like this. This is a different functional description. Even here, it starts at time equals 0, and so the maximum force starts out here and then falls off as the meteor digs into the Earth. But again, you can pick an average force, and here you can see visually that the maximum force and the average force are of course going to be very similar, are going to be within a factor of 2 of each other. So there's not going to be, it depends what kind of precision you want, how much of the mathematical trouble you want to go through. Now, one question you might ask is, well, where do we get or delta t of 2 seconds from? So this is one, you know, there's some estimation here that is going on, of course, but one of the things we know is that it's probably going to be faster than 10 seconds. It's probably going to take longer than a microsecond. So we can disagree about the exact number we use there. But one typical number that people use is, if you're going with a certain velocity, then how long does it take you to traverse a characteristic length of the object? So the textbook has another example, which is dropping an iPhone. If you were to drop your iPhone, I guess iPhones have rounded corners, right? So if you drop your iPhone on the ground, the time interval it takes for the iPhone to come to rest is the time interval it would take for the iPhone to travel its own length in with the velocity it will have by the time it reaches the ground. So that gives us a length, and then v initial for the interaction where it bounces off the ground, the L over V initial will give us the delta t. So the other things, the other numbers here, the size, the mass, the density, those are things we can estimate based on other meteorites. In fact, for this particular meteorite crater, the meteorite is actually buried underneath the crater, so you can take samples and measure the density, which would be one piece of information that you can help to improve your estimate. Okay. So one other aspect of impulse is relevant for airbags. So one thing you'll so this is essentially the same problem, except the meteorite is the car and you're in the car, and you're coming to rest against a wall, also known as a collision. So let's say you're starting with an initial velocity of 27 meters per second. And let's say you collide against this wall, so your final velocity will be 0. The average force with which the wall is working on the car, which the wall exerts on the car, is going to be that same initial momentum minus final momentum, so the change in momentum over delta t. So let's go to car bags. Is going to be this example, excuse me. So the average force is the change in momentum over delta t. So that's going to be m times v initial over delta t. So that's the force that is working on the car. Of course, there's going to be a force working on yourself as well. And if you're not wearing a seatbelt and you're not wearing an airbag, then you will hit the steering wheel, and the force will apply in a time interval that is relatively short. So no airbag, no seatbelt. Then let's say that, or delta t is not 0.1 milliseconds. Let's say it's 0.1 seconds. So you hit the steering wheel, bam. So that's a short time interval, so the average force will be high. So now if the airbag deflates and inflates and deflates, and the seatbelt holds you back. So what this does, it actually slows down or increases the time with which you're feeling that force. So the airbag is exerting force on you, and the airbag is of course much larger than the steering wheel, which would be the thickness of the steering wheel, which would be the characteristic time scale that is involved here. In addition, the car is crumpling in a way to also slow down more gradually. So this collision will actually cause a delta t that is probably more like 2 seconds. So the F average will be much lower. In fact, if you take the ratio of this and you look at the expression here, you'll see that because there's a factor 20 increase in time, F average is 20 times lower. So the reason for seat belts, for airbags is exactly to spread out the impulse, which you can't get around, over a longer time interval to decrease the average velocity, the average force that you're experiencing during that time interval. So the total amount of force times the total time over which the force applies is the same, but you're just spreading out a smaller force over a longer time interval while the collision is happening, in the case of the airbag, and that of course allows it to do less damage, and it ultimately gives you a higher probability of surviving. So that's everything for today about impulse and collisions, unless, did I have one other slide? I guess I did have one more slide, but we kind of went over this, which is that the change in momentum is equal to the impulse. So you can of course write that in two-dimensional vectors as well. So in this case, if we kick the ball downwards here, and there's already an initial momentum here, then that will give the ball an extra, give it a change in momentum that is equal to the impulse, and that will cause the final momentum to be larger in that direction. So, but that's all for today. Next time we'll start talking about conservation of linear momentum. So in many systems we'll have conservation of momentum, much like we had conservation of mechanical energy, and we'll use that to actually analyze collisions between objects where there can be either momentum conserved or there can be no momentum conservation, and then we'll distinguish those two situations. Okay, and that is it for today. So we'll talk to you all on Wednesday.